Hi, I'm Bianca Coker from Region 10,
And I'm Andrew Burns from Dallas ISD.
and today we're here to talk to you about one of the new math standards in 8th grade, 8.4b. 8.4b reads, the student applies mathematical process standards to explain proportional and non-proportional relationships involving slope. The student is expected to graph proportional relationships interpreting the unit rate as the slope of the line that models the relationship.
Now, Bianca, I'm hearing you say proportional and slope, and so whenever I hear slope, that's a huge word in algebra. So is this in the proportionality strand or the algebra strand?
Well, actually, Andrew, it's in the proportionality strand, which is kind of funny because this is straight out of Algebra 1.
Right.
So it's pretty interesting. I think what we're going to be doing in this particular standard is looking at proportional functions from an algebraic point of view. Or maybe algebra from a proportional point of view. I'm not sure which.
It's like the chicken or the egg.
Exactly.
I know it's important because a lot of algebra is moving now to 8th grade, and some 8th grade teachers might not have been in an algebra classroom in quite a long time. So this is important information.
In fact, Andrew, I wanted to tell you, when I learned algebra, it was a long time ago, and we learned it very traditionally. Teacher stood at the front, we had worksheets, and we learned procedure and processes, and we really didn't have a conceptual understanding. In fact, I really didn't understand algebra until probably I took some college-level math classes. How about you?
I was the same way. I learned formulas a lot through math and just memorized the formula and didn't really make a connection of why it worked, the different components of the formula. So students, if students don't get that the first time, then I think that they just disconnect from math altogether and have a phobia and develop anxiety. So we really need to differentiate, which means make sure all of our students understand the math. And to do that, we need to teach it conceptually so they can make connections between prior knowledge and other domains of math.
I agree 100%. And what you're going to see in these standards, as well as the rest of the middle school standards, are the concept or the focus on multiple representations and connecting slope in, for example, a table, a graph, an equation, a situation, and we're connecting those together. And with that, we're going to help build that conceptual understanding. So let's get started. So for this standard, we're looking at specifically proportional functions. And when we look at a proportional function, that equation takes the form of y equals kx, where k is the constant of proportionality. That's a little different, isn't it?
Yeah, because I'm used to hearing y equals mx plus b when we start talking about linear equations. That's the first form of linear equations that we learn.
Right, right. And so it looks like it's very similar, y equals kx, y equals mx plus b, but there's a couple of differences. First of all, instead of k, we have m in the standard linear equation. What do you think? Why do you think they have m there?
Well, I've read that the M is from a French mathematician, and it stands for montant, which means climbing. So that kind of makes sense. The slope.
Sure does.
You have to go up a slope when you climb.
Right, right. So excellent. Well, that's good to know.
So why does it go from M to K in a proportional relationship?
You know, I just think that sometimes they want to emphasize that this is a unit rate, a scale factor, a constant proportionality. And so they use K, even though constant starts with C. So
it's not good for spelling. But
No. But that's what we do in math, I guess. So it's just one of those things that we need to expose students to. They need to know all the different ways we could be talking about slope.
Okay, so K stands for what again?
Constant of proportionality.
Okay, but that also is the same thing as
slope,
right? So
scale factor, unit rate, all of those things that we associate with these linear functions.
So multiple representations are important, as well as different vocabulary that they can associate with the different multiple representations.
I agree 100%. I agree. Now I noticed something else, that in your linear function standard equation you have a b. What does that b represent?
Well, the b, I don't know what it stands for. I haven't read that, but I know that it's the y-intercept, which means we have multiple representations. So in the graph, it's where the graph crosses that y-axis. And in the table, it's where we have 0 for the x-coordinate and 0 for the y-coordinate.
So in our constant of proportionality type equation, our proportional function equation, we don't have a b at all. We just have y equals kx.
So it's kind of like saying y equals kx plus 0. So it's an invisible b. It's a 0 for b.
Okay, and that's exactly the way I used to teach my students so that they would understand that if it was a proportional function, it's a special kind of linear function. It's still a line, it still has a slope, which might be called m or k, and that it goes through the origin, like you said on the graph, or that the y-intercept is 0. And so we would see on a proportional function that 0, 0 would always be in the table. It would always be a part of our graph. And we can interchange that m for slope and k for constant proportionality. What do you think?
I think so. So if you see a graph, first of all, it has to be a line to be a proportional relationship. But if you see a line that does not go through the origin, it is not a proportional relationship.
That's right.
That's a dead giveaway for one of those questions that asks, which of the following is not proportional? Well, if it doesn't go through the origin and it's not a line, it's not going to be the answer.
It can't be right.
Right, thank you.
And it can be linear, but not be proportional.
Right.
Because proportional are a special kind of linear functions.
Just
like squares or special kinds of rectangles.
There you go.
All right, good. So let's move on and look at an example. My daughter recently traveled to London, and she bought some souvenirs, and she used her birthday money, thank goodness. She bought some Earl Grey tea for her father, and that was 8.5 euros. And then she bought a Pandora charm for her mom. 25
you
euros.
Got a present.
I did. And a t-shirt for 4 euros. She was excited because it was really cheap. And the exchange rate was 1.39 US dollars. And so what happens when you purchase things overseas, if you use your debit card, you get charged 8.5 euros, say in London. But back here in the States at her bank, it took out the equivalent amount of US dollars. And so for her to understand how much she was really spending in US dollars, she needed to know the exchange rate, which was 1.39. So I've thrown that information into a table here. And as you see, we have the amount of euros as our input variable or independent variable, and then we have our US dollars as our dependent. And what I did to make this table is I multiplied each amount of euros by the exchange rate, kind of like a scale factor of 1.39, and then we get our amount of US dollars. So those were actually the amounts that were taken out of her bank account.
That's great. And 8th graders should be very familiar with this representation. It's a table, but it's got this middle column. It's called 3-column process chart. Sometimes you'll hear that. And it just shows the X in the far left column and the Y in the far right column. And then in the middle, it just shows what's going on. How does that X, what do you do to that X to produce or yield that Y? And that's what's shown in the middle. And we see that common 1.39, which was your exchange rate. So if you spend a euro in London, you spend $1.39 in the United States.
Exactly. And so when we look at that situation, we can even come up with a function rule where we have euros times 1.39 equals dollars. And we have our nice little equation there. So that's pretty easy to understand.
I think we might have that equation.
Well, later.
Not yet.
I tricked you. I did want to show you a graph of this, though. This graph shows the 3 points from the table, and I put a line through them because they look like they lined up nicely. But you have a problem with our graph, don't you?
Yeah, because right down there at where the x-axis intersects the y-axis, I don't see a 0, 0. I see maybe a 2. So, but I think it's pretty close. So.
I think we can anticipate that if I spent 0 euros in Europe, swiped my card, and they charged me 0 euros, that they wouldn't take anything out of my bank account, right?
Right.
So I'm pretty sure that if we put 0 in for our input, our output would be 0. So we would have that all-important 0 for our y-intercept to make it a proportional function.
Right, and that's important that you have to, if you see 0, 0 on the graph, that's one representation. 0, 0 on the table, that's another representation. But then you have to think, what does that mean in real life?
Right.
If I spend 0 euros, I should be spending $0.
Let's hope so.
Yeah. Otherwise, they're cheating you.
They are a little bit. Yeah. And it could happen, so you got to watch. All right. So let's look at this graph and look at what the slope of the line is. So typically when we do the slope of a line on a graph, we can do things like rise over run, but the official wording is we do the change in the y divided by, or the ratio of the change in the y to the change in the x. And so one of the ways we represent that change is with this Greek symbol delta. So delta y divided by delta x is our fun little shorthand for representing the change in y divided by the change in x. And so if I go from the first point up vertically, I'm going from about 4.5 to about 12, so that's maybe it's 5.5, about 6.5. And then if I go horizontally over to the next point on the graph, I go from 4 to about 8.5, which is about 4.5. And when I divide those, I get 1.44. It's a little different than 1.39. So what do you think I did wrong?
Well, you went ahead and rounded to easy numbers
I did.
because those numbers might not necessarily be 4.5. It might be 4, whatever it was, 4 and 30 something cents.
Right, right. Remember, our numbers weren't quite as pretty as they could have been. So in this situation, I think we're pretty close to our 1.39.
And it's important for students to see not pretty numbers as well.
Definitely, definitely. So if we go back to our table and we look at that, there's one other thing I wanted to show you about that. I didn't really emphasize before our equation. From the bottom row of our table, we can come up with our output, or number of dollars, is equal to that 1.39 times our input. And that 1.39 again was our exchange rate, our unit rate, and now we find it's the slope of the line, so those things are equivalent. And comparing that to our y equals kx equation, can you tell me what our relationships are?
Yeah, I think the D, which stands for dollars, is our dependent variable, or our y value, so it matches up kind of on top of each other right there. And then the 1.39 is the K, which is the slope, or the constant proportionality, or the scale factor, or the unit rate. And then the E lines up with our X value, or our independent variable.
I think you're exactly right. And just for emphasis, K equals 1.39, but that's also our slope.
Right, which was close to our 1.44 estimate from earlier.
Good, good. And then one other thing I wanted to show you from the table that's really only about proportional functions, this only works for proportional functions, is that we can actually, and the reason why they're called proportional, is we can make a ratio of the y, not the change in, just the change in y, but the y to the x value, and that's going to be equal all the way down, hence the name proportional. So, for example, if I take 11.82 and divide it by 8.5, we get 1.39. If I take 34.75 and divide it by 25, I get 1.39. And the same thing happens with 5.56 and divide it by 4. This only happens with proportional functions. So if I'm looking at a table and I don't have my 0, 0, to verify that, and I can't tell it's linear, the easiest way to tell something's proportional really is to look at the ratio of just y to x. It's not the slope, it's just the y to x ratios, and if those are all equivalent, then it is proportional.
That's great. So if delta y over delta x is the same all the way down, we know it's linear.
Right.
But if it's just plain old y divided by x, then we know it's also linear, but it's also proportional.
Right.
It's direct variation.
Exactly, exactly. Good. So Andrew, just a real quick question. When students are looking at bundling this process content standards and they're looking at doing real world situations, what kind of problems might they see with these proportional functions?
They're going to see multiple representations. So they could see it in a graph format, they could see it in table, they could see it in real world situations, they could see the equation, or they might even have 2 or more representations where they have to translate between them and make connections within that problem. That's where those process standards kind of make it a little more rigorous than we used to see maybe on TEKS.
Right, right, exactly. Andrew, our time is drawing to a close. I just want to say thank you so much for talking with me about proportional functions.
Thank you as well. I had a great time.
Great. This is Bianca Coker from Region 10.
Andrew Burns from Dallas ISD. Thank you.